Welcome to this little tutorial on KL divergence. I will explain what it is and will show you the step-by-step derivation of its formulation. Simply put, for a given random variable, KL divergence quantifies the difference between two probability distributions. This measure of difference is required when doing variational inference or when we want to represent a sophisticated distribution using a simpler distribution. Let's say x is our random variable and these are the possible states it could take. P and Q are our probability distributions that we would like to get compared. Note that I have used theta to indicate the parameters of distribution P and I have used phi for Q. This also shows that KL divergence does not require that P and Q are of same type of distribution. For example, P could be the student distribution that has 3 parameters and Q could be the normal distribution that has 2 parameters. Here I am showing you a way of computing the probability for x1 using both of the probability distributions that we have. Now most of the time these probabilities or likelihoods that we will compute are going to be small numbers, which will get multiplied with other small numbers, and that may result into rounding to 0. So instead of that, we generally compute log likelihood. Now, one way to understand how similar two entities are is by simply computing the difference. So we can perform a simple subtraction operation here, and if that subtraction results in 0, it means P and Q are identical. Otherwise, that residual number will give us the measure of our dissimilarity. That said, this is another way to represent our subtraction when we have logs, that is using a fraction. This fraction is called likelihood ratio. And the entire entity, including the log, is therefore called log likelihood ratio. Here I have removed x1 and I have generalized it by using a subscript I in the ratio. Now this is fine. This gives us a measure of dissimilarity for maybe one sample from our random variable. But what we are really interested in is a number that can tell us what is the difference on average between our two probability distributions, that is P and Q. Now I use the word average, but really with random variables we do not think in terms of average. Rather we say what is the expected value of a random variable or what is the central tendency of a random variable. So here is a very quick primer and recap of expected value of random variables. For random variables, since all states have their respective probability of occurrence, the average should reflect that. That is, samples that have higher chances of occurrence should contribute more towards the average, and this is why we call it a weighted average. And this is how you would do it for a discrete random variable. In this formulation, x is the state of the random variable and px gives its weight or the contribution towards the average, and you then simply sum up the result. Here the summation is showing that you do this calculation of expected value for a very large number of samples. Here is shown another formulation which is more general. Essentially, instead of random variables, we are computing the weighted average of a function of random variables. Most of the time you do compute the expectation of function of random variables, and is the case for our problem at hand as well, and you will see that. So far we have expected value for discrete random variables. This is how you would do it for continuous random variable. The difference here is that our summation has been replaced by an integral. Now, with the expected value primer out of the way, you should be able to see that our log likelihood ratio is nothing but a function of random variable. And since we are interested in the average of this function, we should be able to use expectation. And so to get its average, we need to first weigh it using the probability of our sample and then simply compute the sum as I showed you earlier. To be correct, instead of saying average of log likelihood ratio, I should say expected value of log likelihood ratio. And this, my friend, is what is KL divergence, which we can also express using the expectation symbol. Now, so far I have shown you log likelihood ratio for discrete random variable. Here is how it would look for continuous random variable. The difference is that instead of summation, we have an integral. This all being said, there is one challenge that we need to address and talk about. The difficult part in this formulation is that for both discrete and random cases, we would have a lot of computational problems. And those stems from the infinity that you see in the summation, as well as the integral goes from minus infinity to infinity. And therefore, we need to take help of one more concept to get around it. Here is another quick sidebar for that concept. The workaround will be made possible with the help of law of large numbers. Here I have put what Wikipedia says. Essentially, it is saying that if you have very large number of samples, then the arithmetic mean of those large number of samples would be equivalent to the expected value of random variable. So here the formulation is shown as well. Key thing to note for you is that n has to be a large number for this approximation to hold true. This means we can also write the expected value of log likelihood ratio, or simply put KL divergence, as the arithmetic mean provided we use many samples. Now note that this holds true for both discrete random variables as well as continuous random variables. So we can use the same approximation. This is another notation that you need to get familiar with. Here D on the left hand side stands for divergence, and KL, you know what it is. Now, so far we weighed our samples using P and got this formulation of divergence. But what if we wanted to use Q to weigh them? In that case, it would look something like this. As should be clear, these two formulations will give you different values for the same P and Q. P and Q have not changed, yet these formulations are going to give you a different measure. And this is a reason why we do not call it a distance, because it's an asymmetric measure, and hence the usage of word divergence. There is also, by the way, a name for these two divergences, and it depends on which one is your reference and which one is your approximation. Generally, we use P for the reference distribution and Q for the approximation. So for that, the first one will be called the forward KL, and the other one will be called the reverse KL. The next obvious question that should occur to you is that which one should you use when, since these give you different measures of similarity. And the short answer to that is that it depends on your application. But let me show you a small example so that you can see the different behaviors that these two KL divergences have. Here I'm showing the plot of a synthetic data that I generated. Since it has two peaks, it's a multimodal distribution. Essentially, I added two Gaussian distributions to get this one. Now our task is to approximate it using a univariate normal distribution Q. I will first show the result that I got when I use forward KL. As you can see, the approximation using forward KL sits somewhere in the middle of the two peaks, and hence we say that it has a mean seeking behavior. Now when I ran reverse KL, the approximation Q got zoned on one of the peaks, and hence we say that it's a mode seeking behavior. Which one is better? It would be tad bit difficult to answer. Now one way I can justify here that reverse KL is better here, at least in this, for this toy example, because it is at least picking up the main mode of the distribution. Now, most of the time when you are doing density estimation and using variational inference, you do use reverse KL. Forward KL is used a lot in machine learning, but you do not see the name forward KL quite often because it is being used indirectly. For example, when you use cross entropy loss in your classification model, you are using forward KL, but indirectly, or at least a component of the KL divergence. And this brings us to the end of our little tutorial. But some of you are wondering, what about the information theoretic perspective? Some of you may know that KL divergence is called relative entropy as well. Reason I have not explained that aspect is because for that you need to first know entropy. I do plan to do some tutorials on that, and then I would provide the information theory view of KL divergence. But if you're curious, you can read it in this article of mine. I'm providing the link to it in the description. The article does provide an in-depth explanation of entropy from few different perspectives, as well as the notion of relative and cross entropy. And with that, I want to thank you for the time you gave here. I hope this tutorial was helpful to you. If you have questions and doubts, please do write them in the comments and I will try my best to answer them. Goodbye. See you again.